Hello everyone. I am going to begin a new chapter called metric spaces. I plan to quickly move over some elementary stuff and begin a full-fledged research level introduction of some topics in metric spaces. Let's begin immediately by recalling what a metric space is. It's simply a set X with a function from Cartesian product of X with itself into real numbers, which we call distance function for simplicity. We will also call points of members of X points of X because we want to think about them geometrically. Anyway, the axioms for D are that D of xy is 0 only if x equals y. We have symmetry in number 2, and for number 3 we have the famous triangle inequality, which says that the distance from x to y is never less than the summation of distance from x to z and then back to y, which generalizes our intuition about geometry coming from the R3 Euclidean space. You may be surprised that in number 1 I don't have any assumption on positivity of the distance, and that comes to this beautiful exercise that actually if you have only 1, 2, 3 as written here, you can conclude that D has to be non-negative. So I'm gonna begin by listing some examples of metric spaces. What I want you to pay attention to is how gradually I get rid of additional structures to end up ultimately with only a set and a distance function, a true metric space with no other structure on it. So let's begin with our familiar real line R1. So what structures are there on this space? There is a notion of addition. There is a notion of multiplication, which turn this space into a field. There is a notion of scalar multiplication. I want to include this because later I want to compare. So if you have x and a real number lambda, you can always multiply. You have a notion of order in it, which is kind of unique for R1. And you have a notion of dot product, so you can dot product x and y, although it's just x times y in this case. And then you have a notion of norm, absolute value of x, which I want to put as x dot product x to power 1/2. And then using this norm, you can define distance of x from y to be x minus y, and then take an absolute value of. So that's our R1. As soon as you move into R2, you lose this ordering that there is a well ordering of this set. However, especially because you can identify it with the field of complex numbers, you still have a notion of addition, of vectors this time. You have a notion of multiplying vectors by identifying them with the corresponding complex numbers. You have this notion of scalar multiplication of vectors. Lambda is real number, x is a vector. You've lost, as I said, the ordering, but you still have this notion of dot product of two vectors, and which leads to a notion of norm by, again, dot producting two vectors and then taking the square root. And then, again, there is this notion of distance coming from subtracting xy and then taking norm. If you move into a generic Rn, you are left with addition of vectors. There is no universal notion of multiplying vectors that produces another vector. There is this scaling still available, the dot product still available with similar definitions. this norm again available, and then distance of xy equals x minus y norm. So you still have a distance function coming from a norm. Okay, but there is also a way to give this Rn a different norm. So Rn together with, say, L1 norm. There are many different norms, but in particular I want to choose this L1. There is this notion of summing vectors, there is this scaling, and this time the norm will have nothing to do with the dot product. So I'm thinking of it as getting rid of the dot product structure, and all I have is a notion of norm, and L1 norm is just adding the components of your vector in absolute value. And you can still define this distance by taking norm of subtraction, and this time L1 norm. So as long as you have a norm, this quantity of subtracting and taking norm will produce a distance function, which you can prove. All you have to do is verify the axioms for distance function using the axioms for what is a norm. Now, moving up, there are infinite dimensional versions of this. So Rn with the inner product can be turned into a Hilbert space. So this is the generalization to infinite dimension of the Rn with its dot product. So this is just an infinite, possibly infinite. You can also call Rn, say Rn is a Hilbert space. So infinite, possibly infinite dimensional vector space together with a norm. With an inner product. So with an inner product, and that is giving us a norm, and we use the norm to define this distance function. But you also have a generalization of this Rn with the L1 norm. So you can have a normed vector space. So it's a vector space, again, equipped with a norm, but the norm, so here the difference to the Hilbert case is that norm does not come necessarily from an inner product. And there is some beautiful theorem which tells you exactly when a norm does actually come from an inner product. So all of these, again, are examples of metric spaces with distance defined via the norms. However, you may wonder, are there metric spaces where the distance function has nothing to do with the norm? And definitely there are. So one example will be manifolds. So think about R3 and any manifold sitting inside R3. Then it's not a vector space because, for instance, if you are at this x and you scale it, you leave the manifold. So twice x will be somewhere here outside of x, which you don't see. Or there's no notion of adding x to y within x. So you can consider them as points in R3 and add, but it has nothing to do with the space x you start with. So x inherits, so x sitting inside R3 inherits the usual distance. That means if you wanna say how much the distance of x and y are, you regard them as points in R3. But there is no notion of adding vectors within x. So per se, X is not a vector space equipped with a norm, so definitely the distance has nothing to do with a norm. Of course, a general manifold does not have to be embedded in R3, so you can think about an abstract manifold where even with cheating there is no notion of adding two vectors, 2 points in your space. But actually, to get rid of every possible other structure, we need only to look at finite metric spaces. These are metric spaces with cardinality finite. A bunch of points with some distances defined between them in an abstract way, so they don't even have to be regarded as sitting inside Rn. Interestingly, there are some finite metric spaces that you cannot embed inside Euclidean spaces. That means you cannot represent those set of finite points inside a Euclidean space and realize the exact distances that they have from one another. That's probably an interesting exercise for you. But anyway, you see that there's no way you can come up with a vector space structure on such an object. There's no scaling on this, so this is truly a set X with distance function. So I plan on introducing you to more interesting metric spaces in a future video, and I will cover topics as diverse as group theory, edit metrics, and whatnot. But meanwhile, I encourage you to reflect on how general metric spaces are, and that makes them prevalent everywhere. So any technique, any theory that we develop on general metric spaces will be applicable in many different situations. For instance, we have this contraction mapping theorem that if you have a contraction between a self map on a complete metric space that is a contraction, then it has a unique fixed point. And the applications, of course, are just everywhere. As long as you turn some space into a metric space, this theorem can apply. So we've seen applications of that into a space of functions where you define distance of two functions, say by a supremum norm or by an integral of their difference. And that makes this theory of metric spaces fascinating. And again, I said that I plan to quickly move into research level topics in metric spaces. So in particular, I want to cover the notion of Hausdorff measure, which generalize the notions of length and area to such abstract settings. Just imagine that. There is no other structure whatsoever, but still we want to come up with a notion of measuring area and length. I want to cover some interesting metric spaces like Heisenberg group. I want to talk about embeddings of metric spaces into Banach spaces. And well, once we move and get pretty advanced, I can talk about area formulas and co-area formulas for maps into metric spaces, and the possibilities are unlimited. Hope to see you in future videos. Please subscribe to my channel if you have not yet done so, and very excited about metric spaces. See you soon.